Okay, the purpose of this video is to sort of understand what's going on with the Lagrange error bound. Here's e to the x, 1 plus x squared over 2 factorial, the infinite series. First thing you want to recognize is this infinite series is exactly equal to e to the x. But normally what I do is I'm going to say, in this case, I'm going to try to estimate e to the point 2 using the fourth order up to the fourth derivative. So what you should recognize is P4 of x plus R4 of x, which is all the remaining terms, is equal to the entire infinite series. So R4 of x by our Lagrange theorem is equal to the absolute value of the fifth derivative evaluated at this c, where in this case c is between where it's centered 0 and 0.2 times x to the fifth over 5 factorial. So the maximum of the fifth derivative is at 0.2. So this error exact, I say, is less than or equal to the bound, because the highest that c, this f5 of c could be, is e to the 0.2. So I know that this error, which is equal to all these terms, is less than or equal to this, which is this very small number, 0.0000326. Now, just for kicks, I did calculate the exact error using the calculator, minus, again, the first 5 terms using 0.2 for x, and I got 0.000002758, which is less than that, which is what we'd expect. But now I want to talk about sine of x is equal to x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial. Now this is an alternating series. So if I just say in a problem, give me a good error bound, and I say I'm going to use the first 3 terms to estimate sine of 0.4, then the error is equal to the absolute value of the first neglected term. That's from our previous information. So in this case, it would be the absolute value of x to the seventh over 7 factorial, which I calculated with 0.4, is equal to this very small number you probably can't see, 0.000000325. Very small. But you can also be asked with an alternating series to give the Lagrange error bound. So the Lagrange error bound, if I'm using the first 3 terms for sine x here, would be R5 of x, I'm going out to the fifth derivative, is equal to the sixth derivative at c, where I'm calculating c between 0 and 0.4. The sixth derivative of sine x is negative sine of x. So again, I'm going to say this thing is less than or equal to, what's the highest value on 0 to 4 of sine x? Sine of 0.4 times 0.4 to the 6 over 6 factorial. And for this, the Lagrange error bound, I get 0.0000215. So, summary. If you got all positive terms, you have to give the Lagrange error bound. If you got an alternating series and I just say give me a good error bound, you can take the first neglected term. If I do have an alternating series though and ask for Lagrange, you're forced to this. Now you might want to shut your ears to this, but those of you who are interested in nuance, when I have sine of x, I said I'm going to stop at the fifth. So it would be, the Lagrange error would be the sixth derivative of c. Now, can you see with this, I could have said, well, what is R6 of x? Because if I go out to the sixth derivative, that's going to be this term right here, which is 0. So I could have said R6 of x is the seventh derivative at c times x to the seventh over 7 factorial, and got even a lower bound. Don't get stressed about that. In conclusion, all positive terms, you have to do LaGrange, but I want you to understand that what I do when I say it's equal to this, then I bound it by choosing that C. So the error, this, all these remaining terms, definitely less than or equal to this number. And then when I have an alternating series, I have two choices. The easy one, first neglected term, but if I do ask for the LaGrange form, then you have to do that. All right.